chapter 3 finished. I hope that's my goal. Got a lot of notes to do. Sorry about that, but you know, some sections, there's lots of things, terminology and ideas that we need to kind of write down, or else we'll forget them. And so that's what is happening for a large part of today. Okay, so chapter 3, regression lines, continuing from where we left off. Got a kind of summary of some of the things that we've already covered. Here's a scatter plot, a nice straight line through it. WebAssign has decided that this straight line is called the regression line. So you hear the word regression line, they're talking about this guy. They could have called it least squares line, best fit line. Remember all the lists I gave you, in case you watch videos and you're wondering, you know, what they're talking about. The x-axis is called the explanatory variable. The y one is called the response. We know about that. We know about the correlation coefficient, normally written as in a decimal. So let me just do a quick summary of that guy. If you have a perfect straight line going upwards, then the correlation coefficient R is 1. So the correlation coefficient is a decimal that it always takes a value between -1 and 1. And a perfect 1 is a straight line going this way. A perfect straight line going down the way would be a correlation coefficient of -1. And if you got some data that had nothing going on at all, it would look like that. We're all familiar with those expressions, right? So there's a new guy in town, which I don't think I've mentioned. If I did, it's very fleetingly. And it's called R squared. It's a good name because to calculate it, you take R and you turn it in, you know, you multiply it by itself, right? And typically you will turn it into a decimal, not into a percentage, sorry. Normally you would write R squared as a percentage, but it can be written as a decimal as well, but typically we like it in a percentage. So suppose I had a correlation coefficient of 0.9. Then R squared would be 0.9 times itself, which is 0.81, and we would typically call it 81%. R squared is also a measurement of how good the data is to being a perfect straight line. Right? 81% is pretty high. R squared, if you write it as a percentage, always takes values between 0 and 100%. How come you don't get negative numbers out of R squared? What's the reason behind negative numbers never have?
Because a negative times a negative is just a positive? That's
a better reason, yes. If you take a negative number times itself, don't you always guarantee a positive answer out of that? Would you agree that 0% would be this fella? 100% would only mean a perfect straight line. But couldn't it be a perfect straight line going down the way or a perfect straight line going up the way, right? As I said, it's typically written down as a percentage, but if you want to think of it as a decimal, won't it take values from 0 to 1? Now I'm going to show you 2 questions involving being told one of these 2, and your question is to find the other one. So for my first question, suppose I tell you that R is 0.8, and I ask you to find R squared. Would you agree that's pretty easy to do, right? You just take 0.8 and you square it, you get 0.64, and we'll call it 64%. Everybody's happy. Let's do it the other way around. Suppose I tell you R squared is 0.81, and I ask you to find R. Oh, my apologies. 81%. That's better. And I ask you to find R. There's a couple of things. First is there are a lot more work, which is kind of what I did by mistake there. Your first thing you must do is turn it into a decimal. Now, what should I do to this decimal to find R?
Square
You run
root.
it through the square root.
Okay. Now, when you take the square root of this one, you are going to say, got it, and you're right, but you're only half right. Couldn't it also be that one? Could be down the way as well as up the way. Do you notice then that you can never be 100% sure which of these two you get? Right, 81% could come from a line with an R of 0.9, but it could have came from a line with an R of negative 0.9. There's no way of telling, unless you were given maybe the table that it came from or the picture of the scatter plot. Wouldn't that be a good idea? So suppose this question came with a picture that looked like that. When you choose this one, if this was the picture that question came from, why do I pick this fella as the right answer rather than the positive one?
Because it's a negative slope.
That's it. Go for the obvious first, because it's always a good sign. Oh, and I almost forgot, it's not a biggie, but I forgot. R squared is sometimes called the coefficient of determination. I don't know if this textbook calls it that, but it is a pretty common term. So if you watch a video and the guy says the coefficient of determination is 81%, do you know he's just telling you this guy, right? Just so you're used to the name. Okay, now, suppose I tell you I have R squared and he's 10%. I have an R squared of 80%, and I have an R squared of 99%. Just 3 examples of R squared. One of the ways that you can use R squared is it's a measure of how good the data is to being a straight line. Would you agree that this fella here would have probably have came from a picture that looked virtually like a straight line, right? Maybe a couple of points shy. Something that looked like that. Oh, by the way, this could have came from a perfect line going this way with a couple of points short, right? We don't know which, but we know at least it's very good. Would you agree 10% is probably darn close to being nothing much at all? Right? 80%, pretty good, right? Now, there's a sentence that we sometimes you'll see used, and there's various versions of it. So here goes. If you are told R squared is 80%, the sentence it goes something like this. This means that 80% of variation is accounted for by the model. I know that is very like a lawyer wrote it in a way, I guess it is. If you want to put it kind of in more English, if R squared is 80%, you can think of it like 80% of the time, isn't that line going to be pretty close to the real answer? Right, if you used it to predict something, 80% of the time it's going to be darn close. If you use this one, wouldn't it be 99% of the time darn close? Wouldn't there just be a couple of points where it might be a little bit out, but 99% of the time it's a good fit? So I think thinking it in that way helps, right? If I collect data and the R squared is 99%, that's probably very good at predicting the truth, right? It's going to be a really good fit. On the other hand, if R squared was 20%, shouldn't it be very wary on trying to use the equation of the line to predict anything? Because if you're only going to be right 20% of the time, doesn't that mean 80% of the time you're likely to be wrong? You got to think of it as a two-way street, right? 20 right means you're 80 wrong. 99% right means you're 1% wrong, but you're never going to be perfect, right? 1% wrong is pretty good. Any questions about that before we look at some of the homework questions? We feel good? Because some of it's overlapping. We've mentioned it before, and that's not a bad thing. If you hold on a second, I'll have it set up for us. And here we go. Maybe make it a little bit bigger. Oh, that's not too big. That'll work. Maybe one less. Can't read the end of the sentence. I can do it now. Okay, here are 5 decimals. Which of these following could not be a correlation coefficient? Which of these could not be R? Just shout it out. Which ones could not be R?
2.2.
Agreed?
A negative 1.4.
Agreed. Because they're bigger than 1 or less than -1. Right. Same question, but be careful. Now it's R squared. Now R squared typically can be written as a percentage, but it can be written as a decimal. So we'll break the question into 2 chunks. Looking at the percentages there, which ones could not be R squared?
Positive
Plus
200%.
200.
Yep, and?
Negative 50.
Yeah, we're all in the same place. Agreed?
Mhm.
That's good. Right, now focus on the decimals. Who are you going to kill off in the decimals? For R
1.7.
squared. Yeah, and what else?
Negative 0.25.
Agreed. Now, isn't negative 0.25 okay for an R value, but not okay for an R squared value, right? So there is a difference between what you can get in each situation. Now, this one here refers back to these. So looking at these ones here, which of the legitimate values? So that means only these 4, right? 0, 0.31 and 25%. Which of those is the strongest relationship?
1.0.
Agreed? Isn't that the perfect relationship? Which one of those is the worst one?
0.
0.
So when you come down here, you're going to pick like a 1.0 and maybe a 0 if it was the other way. So far, so good. And another thing just came to me. I've wrote it down in those notes, so if you've got the notes, you'll see it. I didn't speak it out loud. The correlation coefficient R and the other guy, the R square, are independent of the
Hello?
units used. Hello.
Sorry, I thought my mic wasn't working. I was just trying to ask if R2 values they're always positive, right?
Correct.
Okay, cool. Thank you. Sorry, I think my mic stopped working for a second.
You're fine. Oh, while you're doing that, some people are unsure of how participation goes. Turning up in class is what we're calling participation. I'd like you to answer questions and ask questions, and that's great. So when you get your participation grade and it says 2 out of 3 days, that means that I've only got a record of you being here for 2 out of 3. Now, that doesn't mean that you weren't here for 3. It might be that I just missed it because I have to scan through, up and down, because nothing's alphabetical. And so if you find anything that's inaccurate, you can tell me. I'm making up week 2's report. So if you want to wait till week 2's report is through and then tell me about it, I record everything so I can just go back and look, right? So it's not I can't check it. So if you were here and I said you weren't, we can fix that. Now, back to R and R squared are independent of units used. Can you imagine you do a scatter plot where it was months and feet, right? So an animal, how old it is in months and how long it is in feet if it was a snake. Couldn't you do it in years and centimeters? Couldn't you do it in days and miles? I don't know, right? Can you do any units you like? R and R squared are the same number, regardless if you measure things in weeks, months, days, or seconds, or feet, miles, centimeters, or kilometers. They are independent of the units used. That is important. If you do a scatter plot, can't you adjust the scales to make things look more spread out or less spread out? Can you do centimeters instead of kilometers because it looks better, right? And you'll see it and it looks better than maybe it is. But you can't lie to R and R squared because they don't care what units you use. It's the same number every time, which is pretty impressive, right? That it does that, which is why we like it, you know, because it takes the guessing game out, right? You look at the R, or if somebody says the R square is 90%, aren't you happy with that guy? It's a good model. If they says it's 9%, aren't you going to say, you might as well guess? You know, that model's no use at predicting anything. Yeah, regardless of what its picture looks like. And, oh, are you looking at question 3 now, I hope? Have we got question 3 on the screen? Okay, right. And I'm going to have to shrink the size yet again because evidently you can't see everything. There we go. For 188 students, the correlation between the fastest ever driven and a random number between 1 and 10 is about R equals 0. Not a surprise there, right? Describe what that means by picking one of the following 4 sentences. If R equals 0, what would you be able to say? Which one of those 4 describes it?
The second one.
Are not linear related. Agreed. And a scatter plot will likely show no visible pattern. Would you all agree that that's essentially what that's saying? You know that you get 5 guesses in homework. Will you please not guess 1, check, guess 2, check, guess 3, check, guess 4, check? I know you're smiling because maybe some of you have done that, but it's not a good way to learn. Agreed? Read the choices, get it right, and that means you know what you're doing. Okay. In question 4, suppose that R squared was 100%. Which of those 4 sentences that go below is that telling us?
The second
2.
one.
Yeah, wouldn't it be a perfect linear relationship?
Yeah. And all the points would be on the line. Exactly, right on the line, not near it, but bang on it. Now, what between these 4 choices, right? So R squared is 100%. Between which one of these 4 would the correlation coefficient be? That's the R guy. So if R squared is 100%, what do you get for R?
Either
one or
negative 1
negative
or
one.
1.
Agreed. Right. I wish that question had been like 82% or something so you could do some calculations, but you know, it's fine. It works. Now, question 5. There are 19 female bears and they found a correlation between their chest girth and their neck size. So as their chest get, you know, bigger chest, taller bear, right? So if you wrap the tape around it, not that anybody in their right mind should ever do that to a female bear, that's what you get. And so it's a pretty decent R, isn't it? Pretty high value. So it's a pretty good relationship. Yeah, if you're a big this way, bears tend to be big vertically as well. Yeah, I could believe that. Now, describe how the neck size will change the girth size. Right, if one of them gets bigger, shouldn't the other one also get bigger? So that would be my sense. Assuming that there's no outliers, the relationship is linear, explain what the strength does. The value of this indicates a strong association since the observed data is close to being 1. Would you agree? Just try to put words into a sense. Now, suppose you measured this connection, this correlation coefficient, but instead of doing it in inches, you changed it and you measured it in centimeters because you were a Frenchman. What would the R value be?
0.89. It doesn't
Remember,
change.
remember my sentence about independent of units? If R is 0.89, it's 0.89 no matter how you measure it. It's a very useful thing to do. Here's a very easy question, but it's there. Which one of those 2 implies a stronger relationship?
Negative
Negative 0.6.
Agreed. We don't care it's plus or minus. Isn't negative 0.6 means it's closer to being a downwards line then 0.4 is closer than being a sloping upwards line. Now, here we have a correlation, a scatter plot, and a correlation of 0.95. Yes, Isabel, question?
Real quick, can you go back up for a second to
Sure.
the one that you were just talking about? You said it was negative 0.6
Correct.
because it's closer to 1, or because
Yeah,
it's
well, it's closer to
closer
negative.
to negative 1.
Correct.
Okay, cool. Thank you.
The closer you are to the outsides, the stronger the relationship is, the closer you are to being a straight line. On the one side, positive straight line, right? And the other, a negative straight line, but it's still a straight line. Right, this one is, you stretch your thumb to pinky and you measure it, and you stretch it on the other hand and you measure it. Well, someone else does because your hands are full. It's a very strong number, 0.95, and here's what the picture looks like, and this is good. First question, I hope, is straightforward. What would the correlation coefficient be if you measured that in inches?
0.95.
Yes, 0.95. But independent of units, it's another one of those questions. Explain how you arrived at that answer. I'll let you figure it out. Oh, I like this question. I've done it with other class. Here are 4 scatter plots. Which one of those 4 guys, right, has the strongest relationship to a straight line?
2.
Number 2.
We all agree on 2.
Yeah.
Yes.
Now, you see graph 3 is a very nice looking line, not a line, pattern, right? But it's not that close to being a single straight line. Would you agree? I guess it looks like 3 horizontal or 4 vertical lines, but not one line, right? So I'm picking that guy and I agree with you. Which one of the 3 that's left is the worst?
Graph 4.
4.
Would you agree? Big blob of nothingness? That's what these are. Here's the same basic pictures, but difference, you're going to get numbers. So all good. The numbers.
When I plugged it into that and checked my answer, it said that it's graph number 3.
Ooh, we'd have to argue with 3. Why do they think 3 is worse than 4? Because 3 is made up of 3 straight lines and 5 vertical lines, or 4 vertical lines.
And I guess
Okay, if you do a sausage round 4, it does have a vague direction to it. If you try to do something like that, could this line go diagonally, horizontally, or vertically? And every single one of them is just as good or as bad as the others. Would you agree? Yeah, I'm not really convinced. I wish they'd put a couple more dots maybe here. Would you agree that's got a kind of shape going vaguely that way? Okay. I'll not argue with it, but I wish that picture had been less bubbly or something, right? More direction to it. Now, we're going to do it with numbers. Well, we've already got a head start. Which one of those 4 is negative 0.9?
Number 2.
Yeah.
2.
So that one's going there, right? If these 2 are bad and this one is bad, just out of who's the next number down? In other words, who's going to be 0.6?
Graph number 1.
Agreed. Only because the other 2 are worse, right? That's the only reason. Now, since they've told us that that's even worse looking than this one, and I don't think they changed the picture, can we make this guy 0.3 and make this guy 0 then?
Yeah.
Okay. Now, 0.3 looks pretty big, but isn't that very weak? Remember my scale of R values. If you do an R squared on it, can you trust me that it's 0.09? It's 9% fit. Would you agree a 9% fit is horrible? So
Definitely not exceptional.
right. So I'm more inclined to agree with them, I guess.
I'm not quite sure what's going on with my WebAssign, but every single one of those answers it said was wrong.
Okay, so graph 2 is, right, match these correlations. So let's see, graph 2 should have been negative 0.9. So graph 2 is negative 0.9. Graph 1 we decided was going to be the 0.6 guy.
No, actually, I think, never mind. I put them in wrong. Oops.
Okay, so but you figured out what you've
Yeah,
done,
yeah.
right?
I
You're
figured
good.
out. Yeah.
Right,
sorry.
that's fine. Okay. So moving on to 10 then. A data set of body temperature gives the age in years and a body temperature in degrees Fahrenheit for 100 blood donors in the age group 17 to 84. Okay. This data shows a correlation between the age and body of negative 0.3. Okay. So the older you are, your body temperature is going down a little. Yeah, okay. It's not a great relationship, but evidently it's there. So this indicates that the average normal body temperature goes down with a, well, what do you think negative 0.316 is from those 4 phrases?
Somewhat weak.
Could do it. I'm going for very weak, and if it doesn't like it, I'm doing somewhat weak. A bit of a judgment call going on there. Okay. Here we have, is it 4 stories? We'll do a couple of them. This one is verbal skills against age of children, right? So you get age of children, you get verbal skills, right? And on average, the verbal skills of children who are under 12 tend to improve as the child gets older. Thus, we would expect a positive correlation. Does that sentence make sense? Right.
Yes.
Right. So that's what you're going to do. You're going to try and put together the 2 things. So I'll do the second one. Adult height of a firstborn twin against the adult height of a secondborn twin, right? So identical twins, and you measure their height at various ages, I guess, right? So on average, the average height of the first twin tends to be about the same.
It says the adult height. I mean, I don't know if that's very different, but
No,
I wasn't sure if that changed it.
no. So by the time they get to adulthood, would you agree that the identical twins are probably going to be about the same height?
Yes.
Right. Thus, you would expect the pair to have no real correlation. Right? Or a positive correlation or a negative. Which are you going for?
No correlation.
Okay, do a check on that and see what you have. Question 12. The R value is 0.7. If you want the R squared, you go 0.7 times 0.7 and you get 0.49. Now, they say round off the answers to 2 decimal places. I'm making the assumption that since they didn't mention percentages, that they want the 0.49. If they did want the percent, shouldn't they have at least said it here, or they put a little percentage symbol outside the box, which is what they typically do. So I'm going with that one. Now, if you read later on, can you see it's now 49% the way I would have expected it? Choose the sentence that interprets what that R squared of 49% means. There are 4 dots, 1, 2, 3, and 4. Maybe make it a little bigger for those whose screen isn't great. There. Which one of those 4 is the one we're going to do?
Is it the first one?
Let's check it. The height explains 49% of the variation in the weight. Let's see who's first and who's second. So it's the correlation between the height and the weight. And height explain that one. Because it's X to Y, not Y to X. I'm 90% sure I'm right. If you changed everything into kilograms, wouldn't the R stay the same? And so the R squared would be the same. So it's another one of those. In this one here, 0.16 times itself is not that impressive. As a decimal, it's 0.0256 or 2.5% roughly. And then pick a sentence. Moving on. We are going to do a question using a big table, which I can't see all of it. And they're telling me that R squared is 73.3%. And down at the bottom, they ask you to find R. And I am going to do it two different ways. You can't see it right now, but I'm writing down R squared. Now, it's the temperature in January we're talking about. So I want you to look at the latitude and the January temperature. As the latitude increases, would you agree that the January temperature decreases?
Yes.
So isn't that a downward slope data if you plotted it? And if it's a downward slope, doesn't that mean R is negative? Okay, keep that thought, R is negative. So this is how I would do this question without going near salt. R squared is this guy. As a decimal, is that guy. If you want to get R, you take the square root of this guy. And the calculator comes into play, and the square root of 0.733 ends up being 0.856 and a whole load of other stuff. And they want the answer to 2 decimal places, so I'm rounding it off to that guy. And then I said, wait a minute, wasn't it negative? Remember I said, hold that thought? Negative slope. So don't we choose the negative version of that as opposed to the positive version? Remember, you always get 2 chances, but only one of them is correct for the situation. So not him, him. Okay, so negative 0.86. Got that? Now I'll show you the second way of doing that. I'm going to go into this fella. Here it is here. I'm going to hit use salt. Okay. Which one of these headings do you go to if you want to find the correlation coefficient? Does anyone remember?
Descriptive statistics.
Oh, I never thought of looking there. It might be there. If it's not there, I'm not saying it isn't. I'll have a look in a minute. Where else would it be?
Charts and graphs.
Yeah. Because normally you do that question as a scatter plot, don't you? And so the first variable is latitude, and the second one was January temperatures. And then if I scroll down to the bottom, can you see that negative 0.856 thing that we're going to round off like we had a minute ago? That's where it's hidden. Now you've given me an idea here. I'm going to hit descriptive statistic. No, it's not there, but it could have been. Right? So are we cool with that guy? To 2 decimal places, the answer is negative 0.86, or at least in my data set it is. Now, the next question is not going to really be that obvious. That's basically, that's life. It's the effect that an outlier has on the correlation coefficient and the correlation line. So I think what I'm actually, now I'm thinking about it, it might take me a little bit longer, but I'm going to do it anyway. This is my version of this first diagram, right? This one here. So the data is going to look something like this. And let me show you that. This is something we've not talked about, so you might find it a little bit hard to accept. If that outlier was missing, would you agree that the data is negative and it's sloping down the way? Right. So the correlation coefficient, if you didn't have the outlier, would be some negative number. And negative number means that the data is pointing that way, right? As you'd expect. Now, if you include that outlier, especially if you've got an outlier and there's not a lot of data points, the analogy I want to give is, can you imagine that's a really strong magnet and the line is like a piece of metal? What happens is that the outlier, if it's strong enough, bends the line towards it. Now, I know that the data is pointing this way, but if that outlier is strong enough, can you see it could make it go that way? Which means this is without the outlier. And if you use the outlier, can you see that you could get a line that's a little bit positive? Now, suppose I give you a data set that looks like this, and I put the outlier down here. Right, that's a data set. Can you see it could bend towards it? But would you agree it's still going to be negative? So if you imagine all the places like in a big circle, you know, like a clock face, if the outlier is to the top right-hand corner, right, like over here and over here and over here, couldn't that bend the line towards it? So there are only some places where the outlier will have a really severe effect on the direction of the line. And it has to be pretty big, you know, quite far away. And that's what it does. Have I convinced you that that could happen? Right. If not, will you go for the, I'm a mathematician and trust me, will you do that one instead? That it does do that, right? If you look at this one here, then this is picture one. Can you see that without the outlier, it's negative, but with the outlier, it could be bent to being positive? What about this one? It's negative right now. What would that outlier do? Wouldn't it just change it a little bit, but wouldn't it still be negative?
It might make it a little curvilinear, but it is still negative, yeah.
You'll agree it would almost always make it curvilinear as well. But if we're only allowed straight lines, it will make it negative. Right, would you agree this one is positive? Wouldn't the outlier just make it still positive, just maybe point slightly closer towards the outlier? Would you agree this is positive? Okay, what would happen with that outlier? What do you think might happen at least with this outlier?
Might make it negative.
It might bend it down the way enough. That's something you wouldn't have expected, that an outlier can make your straight line point in the total wrong direction that the rest of the data is saying it. Couldn't that make you believe something that's not true is true because you just looked at the equations and the data? That's why you should always look at your scatter plot before you even think about what you're about to do next. Because couldn't you see the Bill Gates outlier and say, oh no, I ain't using that one. You know, and just throw the data away and work with what's left. Hopefully, at least. Right, now the data in this table gives the square footage and asking price for 9 homes in the county in California. The houses with the square foot, yeah, is obviously an outlier. We've seen this data set before. Remember that guy? Okay. The value of R squared for this relationship is 82.8%. If the outlier was removed, do you think that the R square would increase or decrease? Well, this is another weird property of what outliers can do. So before we answer that question, I'm going to show you the effect that this could have on your answer. And again, it's not intuitive, but it's still true. The answer to what will happen to the value of R if you use an outlier or if you don't depends on the shape of the data and where the outlier is. I'll give you an example. If your data is in a straight line and your outlier is in the same straight line, if you use the outlier, the R value could be that guy. If you take it out, the R value will go down. So if your data is pointing towards the outlier, removing the outlier will reduce your correlation coefficient. And it's to do with the way that R is calculated. You know, like if you use Bill Gates, doesn't the mean go sky high? It's that kind of distraction, right? If you use an outlier and it's in the direction of the data, the R value could go. In fact, I could create some data sets where with the outlier, it's 0.9. And if you take the outlier away, it's 0.1, right? I could make it so severe, you know, all you need to do is make that outlier, you know, 2 streets away from where I am right now, and it would work. However, there are other possibilities, and the effect that the outlier has is different. Imagine same basic straight line, right? But the outlier is over here. Now, in a situation like that, if you use the outlier, so we're using the outlier, the R value might be 0.51. If you took that outlier away, what do you think would happen to the R value now? Go up.
It would go up.
Yeah. So doesn't it depend on where is the outlier before you decide how it's going to affect the value of R, right? Okay, so it could make it go up, or it could make it go down. Doesn't it depend where it is? Also, indirectly, the effect is different in different ways. If the outlier was here instead of here, right, wouldn't this number be a little bit bigger? Would you agree it's an outlier, but it's not as bad an outlier as this? So that might be 0.61. Without it, it would still be 0.91, right? But that might be 0.61. Right, you see how this outlier is here, right? That's the R value with it. What would happen if the outlier was, say, still an outlier, but a lot closer to the data? Wouldn't the data without it change, but wouldn't it change less so? Wouldn't it go down, but maybe only to 0.81 instead of 0.85? Right. So it's not only where the outlier is, isn't it how close it is to the data tells you how strong that effect is. It's still going to have the same effect, but maybe not as marked. So now we're going to have a look at that question. So it took a lot of intro for a very quick answer. This guy is the outlier. Can you trust me that this data set is virtually a straight line and then a huge outlier pointing roughly in the same direction? Okay, so it's positive, you know, bigger area, bigger price, bigger area, bigger, right? Going that way, and then the outlier. And the question asks then, if the outlier were removed, do you think it would increase or decrease? Now, based on what I have just said, wouldn't it decrease? And R would decrease, wouldn't R squared decrease as well? And one of them is the one that you use with the decrease. Now, the next question, 17, also involves notes before we even look at the question. And there are two parts to this. There's the one that you need to do the question, which is fine. And then there's another bit that I want to do because this is a good place to do it. Imagine that you have some data, and this data is the age of a person against their height. And you collect data from, say, 1-year-olds, and you finish at, say, 19-year-olds. And the data is pretty linear. Would you agree that most people, everybody, really, don't you get taller the older you get? Very few people get shorter, at least in the age group 1 to 19, right? Would you agree that's positive? Probably a pretty good R value, right? And just for argument's sake, suppose that the formula for the height was 10 inches plus 4 times the age. So the predicted height was 10 plus 4 times age. So if I wanted to predict what age a 10-year-old is, the model says 10 plus 4 times 10, they end up being 50 inches. Right? Let's say that's reasonable, right? I wouldn't say it was weird. Now I'm going to do something stupid. I'm going to use this formula to predict a 50-year-old. And something really bad happens. Do you see that the answer is ridiculously wrong? An average 50-year-old is not 210 inches tall. And I don't care what country in the world you go to, the average 50-year-old is never going to be 210 inches tall. Do you see that there's a problem that's happening here? And we have to understand why it's happening. And the reason it's happening is called extrapolation. Extrapolation just means using this model, but using it for values, in this case of age, that you never collected the data. Didn't this data basically was 1 to 19-year-olds? Can you imagine what that data might look like or would have looked like if I had decided to collect a bigger database? Well, sure, wouldn't it go up to run about 19 years old? But at that point, don't you kind of stop growing? Can you see that the model isn't accurate anymore? Because the straight line doesn't bear any resemblance to the real answer that a 50-year-old would be. Can you see the problem? That is what extrapolation is. It's using your formula, your model, beyond the range of the data. So if you're only collecting data from 1 to 19-year-olds, it's very risky to use it for a 20-year-old or a 50-year-old or any other year-old. Is it good for an 18-year-old? Yeah. You want to average 10-year-old? Perfect. But don't use it. Don't extrapolate, right? It's a fancy word. Beyond it. Can you see why that might cause problems if people did do this extrapolation thing? Have you ever heard politicians especially using it to give a convincing lie? Well, the science or the data says we have a very strong correlation, 0.9, and the model says that in 50 years from now, we're all going to be in poverty, or we're all going to be unemployed, or we're all going to be millionaires, or whatever it is they're trying to do. Can you see all they're doing is projecting data up to today and then using it to predict 40 years in the future? That's extrapolation, right? I've got model for the data I've got for the last 50 years, but I don't know what tomorrow's going to bring, and neither should they make predictions on it, because isn't that very risky crystal ball, right? But they do it all the time, unfortunately. It drives me crazy when I see them. The predicted answer in the future is going to be Well, if I was that good at predicting the future, wouldn't I have bought Microsoft 40 years ago? Or 30 years, I don't know how old Microsoft is, but wouldn't I have bought it, right? By the way, I didn't. Oh, how do you know I'm not a billionaire?
Because you're teaching
I'm,
school.
I'm still here. As much as I like this job, I am still here.
I was
So-
gonna say that, but then I was like, that might be rude.
Oh no, it's not rude. It's not rude. Have you noticed that I try and be honest? Not honest, or whatever the word is. So if I get bored with something, I tend to tell my students this is boring, but you know, we gotta do it. So I don't see why students shouldn't tell me that as well. Okay, so we're now going to return to this question that's causing it, and then I'm going to come back and talk about the second thing that we haven't actually covered yet, but is very important. And I wish this book had done something about it. I'm going to get in some background sound here, so usual mute, hit spacebar when you're ready. Okay, are we looking at question 17, I hope? Okay, now here is that formula that's telling you, it's to do with putting, you know, if you're putting the ball into the hole, the last shot at the golf hole, right? Yeah, you got really close. And the percentage of time, that just means that the number you get when you're finished is a percentage. Your success rate is 76.4, take away 3.94 times the distance. So when you are 2 feet away from the hole, and you're just going to trust me, I'm doing it on my calculator here. When you're 2 feet away from the hole, it's 76.4, take away 3.94 times 2 feet, and the answer you get is 68.52%. Well, what happened there? I didn't hit all those pluses, did I?
It's super positive.
It's, yeah, I think a cable leaned on my keyboard. Nothing remarkable. That model was probably collected by measuring people, you know, how far away from the hole they were, and then did they get it or not? And, you know, thousands and thousands of people, that's where they got it from. So I'm not surprised that that is reasonable. Now, if you do 20 feet, same formula, but you do 20 feet, can you trust me right now that the answer is negative 2.4%, which is stupid because isn't 0% you're guaranteed to miss? So I don't know how you're getting negative 2.4%. Can you see that extrapolation has killed this one? You've tried to use the model to predict beyond the reasonable range that it was designed for, right? So that is the number. If I was a human being, I'd probably say 0. Right, worst case scenario. But let's assume that they want what they want, so keep it like that. And then you can write down what this is telling you and what that is telling you. So now I'm going to return back to some notes. This is very important in my opinion, although the textbook, I don't know why they don't focus on it at all. I'm going to give you an example of a very important sentence, and it's correlation is not causation. It's a big mistake that a lot of people who don't understand what the data is telling them. Imagine that you had a very strong linear relationship. There's a big temptation for you to say the explanatory variable is the reason for, you know, the response variable, right? In other words, X is causing Y, okay? So here's a silly story, but nonetheless, it's true. I want you to imagine that we collected data on countries in the world. So every dot is one country in the world. And along the bottom, we got the average number of televisions in that country, in a house. Right now, in America, would you agree that most people, not everybody is the same, some people have 0 TVs. My house, we have 2 TVs and there's only me, my wife and the dog. But we have one upstairs and one downstairs. It wouldn't surprise me if some of you had 3 TVs, one for the kid, you know, right? One for you in the living room, one somewhere else. Being a rich country, would you agree we tend to have a lot of TVs on average, right? Now, if you're in a very, very poor country, right, where there's not a lot of wealth, okay, the government, back to my politicians, they probably have a lot of TVs, right? Because they screw everybody else and they take the money and they do what they do, right? They buy houses and live in villas in France, but the usual people who live in that place don't get anything, right? So number of TVs averaged out is tiny. Now, vertically, we're going to do life expectancy. That is basically just the average lifespan expectancy, right? How long you live, right? I think in America, it's about, is it 83, 85, it's 80 something, right? Now you can, let's say we did 90s and 80s, 70s, 60s and 50s. If you took every country in the world and you found out their average number of TVs per household and you plotted their life expectancy, it is not random. Right? It looks something like this. Not a perfect straight line. Would it surprise you that countries with lots of TVs, people in those countries tend to live longer than people who have very few TVs? Would that seem reasonable it could happen? Can you trust me? It does happen, actually. Then somebody says, there's a correlation here, a really strong one. So that must mean that owning televisions make you live longer. The more TVs you own, the longer you live. Now, if that was true, wouldn't you be buying 5 or 6 spare TVs just so you could live longer? If you wanted to cure the problem of low life expectancy in very poor countries, wouldn't you not send them medicine or money or anything? Wouldn't you just send them lots of TVs? Can you see that is not the cause here, right? This correlation isn't saying that TVs cause you to live longer, right? That's not the cause. There's a strong correlation, right, between the two, but not a causation. What, in fact, is the real cause in this data? What's making that happen?
Better healthcare.
Correct. Caused by what? What makes some countries have more healthcare, more doctors, more good stuff like that? Money. Isn't this a reflection on the wealth of a country? Would it seem reasonable that wealthy countries probably have lots of TVs and poor countries don't? But going along with being wealthy, doesn't that tend to mean that you've got as much food, if not more than you need? That you live in nice houses that don't give you the chance of catching the cold and dying with germs because sanitation is so bad? Isn't wealth come along with a lot of benefits? And those benefits tend to make you live longer. And so aren't we measuring the wealth of a country against its life expectancy? So when you see a politician saying this thing and that thing are correlated very strongly, and then they say this thing is causing that thing, that is a very, very big leap in logic. It may be true, but isn't it just likely that there might be some other reason? And we even have a name for that other reason, sometimes called a lurking variable. It has other names. I like the name lurking variable. It's a kind of hiding in the shadows, right? The real reason for what you are saying. Now, you could do this with almost anything. If you made the x-axis time and you made the y-axis the number of children who are tested for ADHD, right? You would find it was positive. And so people would say, things are getting worse. And they might even draw a line through it and say, in 20 years from now, 50% of our children will have that. Or in 100 years from that, all of us will have, all your children will have it. That's them doing the extrapolation mistake. But if they're saying that time is causing it, it might not be. Couldn't the lurking variable be that we test for it more? And each year we test more often. And if you test for something, don't you find it more often? So you've got to be really careful about politicians in particular, who tell you the science says this and that are closely related. And of course, the science then says that this is causing that. Well, you think about it a little bit more before you jump to that conclusion. Because it could be a lurking variable, and try and think of what that might be. And work on the principle that if a politician told you, he's probably lying, right? It's a good motto, in my opinion. Of course, with Daniel. Okay, are you looking at question 18 now? Okay, so here is a big set of data. Here is the equation. Plug in 0, you will get 113.6. So this is nothing about correlation causation, right? This is them just back to their usual. Should this equation be used to estimate the August temperature at the equator? Well, let's be very careful. Wasn't this data collected only from places in America? As far as I know, nowhere in the United States of America is on the equator. Agreed? So shouldn't we be really careful and say, no, don't use that to predict the equator? Who knows what happens if you go further south, right? Other weather things kick in, don't they? Actually, don't you have the Central America? Is Central America on the equator? What part of America is on the equator? The Americas. Is it central? Is it that little isthmus like Panama? Is it somewhere like that?
Ecuador.
Ecuador. So that's slightly north of South America, right? Okay. Couldn't that, if it's close enough to the sea, couldn't that affect the overall temperature? Because sea tends to cool things down, as an example. Right. Okay, this is our next one. Let's see what's going on here. Based on the data for the past 50 years, in the United States, there is a strong positive correlation between yearly beer sales and yearly per capita income. More money, more beer sales. Okay. And 4 chances. I'm not answering that question. 20 then. Suppose that an observational study. Observation. Okay. This doesn't come to the next section, so I'm going to have to tell you what an observational study is in case you don't know. An observational study is where you have no real control over what's happening. You're basically like in a helicopter flying above and watching it, just writing down what you see. So an observational study could be you watch school children, right, little kindergarten kids playing with toys, and you have toys that might have been associated with girls, right, dolls, and toys that might be associated with boys, guns, and you just look at the children and you notice how many girls played with girl toys, how many boys played with boy toys. You just collected data, right? But you had no control of it, you're just watching. That's what an observational data was. Another observational data would be you randomly selected a couple of hundred people and you got them to write down everything that they eat, right, in a little journal. You pay them to do it, right, in a little journal. You don't affect what they eat or how much they eat or anything to do with eat. Don't you just, you take the data that they give you when you're finished. That is observational. The opposite of that is called controlled. Now, a controlled experiment is typically much more beneficial to get good data from. Controlled experiment might be, you get 200 volunteers and 100 of them you give a sugar pill, right? It has no effect whatsoever. And the other 100, you give them vitamin C pills. And you pay them to do it, right? And you wait for the winter to pass and you find out how many colds they got. And one group, they got so many colds on average, the other group got so many colds on average. If both groups got about, on average, 1.2 colds during the winter, wouldn't vitamin C have no effect on stopping you from catching the cold? But if one group was different from the other, couldn't that be evidence that vitamin C stops you from getting the cold? Yes, it could increase your chance as well, right? But it would, at least it would be evidence of some kind. Do you see that that second situation has much more control? And therefore the conclusions are stronger. So back to the question. Suppose that in an observational study, it was observed that the risk of heart disease increase as the amount of dietary fat consumed increases. Okay, the more fat the person ate, the higher, the larger percentage of them had heart issues, right? I can believe that. Write a paragraph to discuss these results does not necessarily imply, correlation is not causation. Yay, they did have one. Since this is an observational study, okay, confounding variable, I call them lurking variable. I like lurking, it's hiding. Confounding is not so. But it's do it, right? Confounding variable. Affecting the, well, let's see the story. The explanatory variable, other than the, got your sentence. Since this is also, there may be confounding variables affecting the explanatory variable other than, oh God, that was a bit boring, the explanatory variable. For example, for those who take a lot of fat, they are higher risk of heart disease. Might also be explained by the fact that they do less exercise, or they might be smoking more. Right. In other words, yeah, they eat too much fat, but don't they do other things? A lot of them do a lot of other things, right? And couldn't it be the other things that they do are a bigger cause for their heart issues? Maybe they eat lots of salty things, right? They take a lot of fat, but they take a lot of other stuff, right? Maybe lots of salty things is the big culprit. Because if you don't know the real reason, isn't it harder to give good medical advice? Shouldn't the medical advice be, okay, we don't like you eating lots of fat stuff, but please cut back in the salt. Because the salt's really the killer, right? If that was the truth. That's how you kind of have to work on this. If you don't know the cause, observational studies don't give you the cause. Good story to tell you. It's a true one. Well, actually, two stories. Connected to medical experiments. We all know, I think we all are convinced at least, that smoking gives you cancer. Would you agree that that is a pretty well accepted thing, right? Smoking cigarettes, they tend to give you other cancers, but lung cancer in particular, right? When that first came out, the cigarette companies obviously didn't want that to come out. So they were fighting tooth and nail, and it took a long, long time to prove it. And the reason was because the only data they could collect was observational. Can you have 200 people that smoked and seen how long they lived and what they died of, and 200 people who didn't smoke and how long they lived and what they died for? Doesn't that take a long time just to collect, if nothing else? Even once they had collected it, they then had to do what they're calling the confounding variable problem. See, people who smoke too much, would you agree that there is a good chance that they might do other unhealthy things, like drink too much, not exercise, eat badly? You know, you could go down the list. So the smoking company said, yeah, we agree that there is a connection here, right? People who smoke a lot tend to get cancer more often. But it could have been for the other reasons that we just mentioned. And it was basically what they had to do is they had to take each one of the other reasons and collect data on it. So let's suppose they went and said they ate too much. You'd have to find 400 people, 200 who eat too much and 200 who don't, but they all smoke. And you looked at the incidence of the cancer. Do you realize that the incidences were pretty much the same? And then you went to exercise. It was pretty much the same. You went down the list till there was nothing left. So it had to be smoking. Now, if you wanted to do that really quickly, you would have to do an experiment, but it's totally immoral. The experiment would be grab 1,000 people at random, right? And they're healthy and they're not healthy and everything else. Randomly put them into two groups and tell the first 500, smoke 200 cigarettes a day. Do everything else you do, but smoke 200 cigarettes a day. And you go to the other lot and say, never smoke a cigarette in your life. And then you follow them. Can you see it? Because the two groups are identical in every other respect, except cigarette smoking, wouldn't the data come out much quicker? Can you see why that is totally immoral? You can't tell people to do unhealthy things to prove they're unhealthy. Right. Second story is one that I got when I was, one of my degrees is in statistics, and I was at Glasgow University. We were told by the professors there that there was a clinical trial, they're called. Basically, clinical trials, what I just said, like you get 200 people. These were people who had prostate cancer, and they had two treatments. One of them got the old treatment, whatever that was, and the other got the new treatment, right? The new pill, I think it was a new pill, right? And they looked at them. And the idea was that if the new pill worked, wouldn't the people who had prostate cancer live longer and maybe even have a reduction in the cancer, right? That was what they hoped for. And they had it all set up. And there's literally billions of dollars hanging on the success of some of these drugs. Because you imagine if that was a new wonder drug for prostate cancer, how much money that company would be able to make when selling that drug for whatever is the first 10 years at exorbitant prices. You can imagine the financial incentive to make it work. Well, they're not allowed to just pretend it worked. They collected data, and after 6 months, the data came back and it was horrible. The people who were getting the new treatment were dropping like flies. The pill had the exact opposite effect. It was increasing the cancer. It was making it more virulent, right? And they were dying, dropping off like flies. And the company wanted the program to continue for a year. And they had to pull the plug on it. Because the company, if you had left them to their own devices, do you want to be in that prostate cancer group who've been given this drug and they're dropping like flies? The reason they wanted a year is they were hoping that the drug was so strong it was killing you. But if you could survive it, it would do well in the long run. Not a good way of, performing your business, right? And so there are health checks. That would never happen in America.